Welcome to College Algebra. In this lecture video, we are going to talk about section 4.3, locating real zeros of polynomials. Now, before I mention any more theorem, I would like to go back to other sections, kind of summarize some of the theorems that we already talked about before. So let's go way back to section 4.1. Okay, so the whole idea of 4.1 to 4.3 is talking about the different ways we can find the zeros. So we could have done it by factoring, by graphing, looking for zeros once we graphed it on the table. And this stay tuned thing is basically the ultimate way. This is what Mr. Chen called the ultimate way to find the zero. So we began talking about different theorems in 4.1 where we have a leading term test that give us an idea, okay, what our polynomial function will look like. And then we talk about even and odd multiplicity on the factors of our polynomial. If a polynomial is factorable, then we can begin to look at the exponent on the factor. It will tell me whether my graph will cross or turn at those x-intercepts. And then we use both of these theorems to do a lot of examples. In 4.2, we begin talking about the division algorithm, okay, long division and the synthetic division. I mentioned the idea of the factor theorem, okay, and we relate the factor theorem with the remainder theorem. So basically what the remainder theorem was saying is when we perform our synthetic or long division, if the remainder is a zero, that tells me that my divisor is a factor. If my divisor is a factor, then the number I use for the synthetic division, the 5, is going to be the 0 to the polynomial. Alright, so what we want is having 0, okay, for the remainder, because that tells me that the number I used was a 0 to the polynomial. Therefore, the x minus c thing, or the x minus 5 for this example, will be my factor to the polynomial. And then we wrap it up, section 4.2, with the linear factorization theorem. I did not really, I kind of talk a little bit about this formula right here. But there was one example, the last example that we did right here, kind of does demonstrate, okay, what the theorem is trying to say. So I'm gonna kind of copy and paste this for a moment, and then I'm gonna bring it, then I'm gonna delete it. So basically what the theorem is saying is, if I have a polynomial, okay, I can write them in linear factorization form. In other words, that I should have nth degree of polynomial can be expressed as a product of a non-zero. So these things that I wrote out is a product of a non-zero constant, and I have n linear factors, okay, where each linear factor has a leading coefficient of 1. Linear factor here means these exponents outside the factor are 1, and all the coefficients were 1. Okay, because I actually took the a sub n to the very outside. So this problem with the leading coefficient -4, I actually just multiply -4 back into my polynomial to actually come out with the actual polynomial for the answer. Alright, so with all these theorems in mind, let me introduce you another one. So again, this theorem in 4.3 got something to do with finding the zero. That square rule of sign is kind of hard to comprehend for the simple fact it's not the theorem is hard, it's just how do we actually use it. Okay, this is basically what mathematicians did back in the day when there was no graphing calculator. that square rule of sign is actually a tool to aid the search for the zeros. It gives a guide to how many positive and negative real zeros a given polynomial has. Okay, real zeros. Because I kind of demonstrated a little bit back in 4.1 where we can find the x-intercept. Okay, these type of answers show up on the graphing calculator. When we graph it, we see it cross or turn on the x-axis. Okay, so those type of zeros are called the real zeros, the one that will show up on the graphing calculator. So this rule just gives us a guide on how many positive and negative real zeros a given polynomial can have. All right. So let my function f of x, all this to be my polynomial with a real coefficient. The rule says, okay, the number of positive real zero of my function is either going to be the same as the number of sign changes of my function, or it's going to be less than the number of sign changes of my function by a positive even integer. Okay, by a positive even integer. Now, if my function only has one variation in sign change, then the function only have exactly one positive real zero. Okay, so what does all that mean? Let's do an example real quick. I'm going to do rule number 2 just in a minute. Okay, looking for positive real zero is the same number of sign changes of f of x. So if you look at this function d of x, this x right now is positive. So basically I'm substituting positive x into every single x I have in my polynomial function. So these given problem already start you off with a positive x. So let's count the number of sign changes from term to term. Positive to a negative, that's one sign change. Negative to a positive is another sign change. Positive to negative is another sign change. Negative to negative, there's no sign change. So that means I have 3 positive real zeros. Okay, count how many sign changes, or it can be less than the number of sign changes by a positive even integer. Less than the number of sign changes. Less than 3. The only even integer less than 3 is 2. So 3 minus 2 would be 1. So that means I can either have 3 positive real integers, 3 positive real zeros, or 1 positive real zeros. Alright, that's for the positive one. Now the number of negative real zeros, okay, of my function is either going to be the same as the number of sign changes of f of negative x. So this time I'm going to substitute negative x into my function. Or it can be less than the number of sign changes by a positive even integer again. If it only have one variation in sign, it only have 1 negative real zeros. So the next step we do is substitute negative x into my function. So that will be 2 times negative x to the 4th minus 2 times negative x to the 3rd plus 3 times negative x squared minus 6 times negative x minus 45. Alright, let's simplify this real quick. Negative x to the 4th power is still going to be positive x to the 4. Positive x to the 4 times 2, positive 2x to the 4. Next term, negative x whole thing to the third power is still going to be negative x to the third. Negative x to the third times negative 2, positive 2 x to the third. Negative x whole thing squared is positive x squared. Positive x squared times positive 3, positive 3x squared. Alright, negative 6 times negative x, positive 6x. Still got negative 45 on the back. So let's see how many sign changes do I have. Positive to positive, nope. Positive to positive, nope. Positive to positive, nope. Positive to negative is one sign change. So my negative real zero only had exactly one sign change. Okay, so that would be my answer. Now why don't we try this? Why don't we go to a homework problem? Let's see if we can find one particular one. I'm just gonna pick a section. Now this is not our section, this is my another section. I'm gonna go to practice real quick. I'm just gonna find an example, maybe something a little bit different. If you can bear with me. Alright, this example, let me make it slightly bigger. Alright. Use that square rule of sign to determine the possible number of positive and negative. Okay, so let's count. So this is already starts you out with a positive x right here. So positive to negative is 1. Negative to positive is second one. Positive to negative is another one. That's 3 so far. Negative to positive is a fourth one. So I got 4, comma, separate multiple answer with comma, or I can have 4 positive real 0, or I can have 2 of them, because the even integer below 4 is a 2. So 4 minus 2 is another 2. Okay. Alright, let's count the negative one. So I got to work this one out. Let me just go to another page here. Let's work this one out. Substitute negative x for all the x's. Let's take a look. Negative x whole thing to the 4 is positive x to the 4th. Negative x whole thing to the 3rd is negative x to the 3rd times negative 4, positive 4 x to the 3rd. Negative x whole thing squared is positive. Positive times positive is positive 7x squared. Negative 16 times negative x, positive 16x. So as you can see, with the last term being positive 12, there is no sign changes. Every term is positive. It's all got the same sign. So I'm going to say 0 here. Nope. Your answer is incorrect. Please choose one of the following. So let's say explaining error again. Did I count something wrong? 1, 2, 3, 4. Make sure my math is right. Sometimes I can get it wrong too. Negative x to the 3rd. Positive. I'm gonna go and submit it, and I'm gonna say, let's see what did I do wrong. I'm gonna go to my solution. Oh man, I messed up with the 0. Because even integer less than 2, that will be 2 minus 2. So that's why I have another 0 there. Now I did not do that earlier. I did not do that earlier with my 3. Because 3 minus 2 is already 1, but 1 cannot minus 2 because there's no even integer. So if I end up with 2, I can still do what? 2 minus 2 to be 0. So the whole idea here is, the whole rule is basically saying, okay, how many positive real zero the function could have. It could have 4 of them, it could have 2 of them, it could have none of them. Okay, how many negative real zeros I can have. For this particular example, it's actually none of them. So what I'm going to do is I'm going to grab this function for you, and this kind of fall back to some of the theorems we learned before. When we see this x to the 4th power by the leading term test, the right side goes up, the left side goes up as well. I'm going to show you. I'm kind of cheating a little bit because I am using a graphing calculator. When this rule first came out, there was no such thing as graphing calculator. So I just want to demonstrate how we can use graphing calculator to help us. So when I use a graphing calculator and I graph it, I should have 4 zeros. I only see 2 cross over the x-axis. So these 2 are real zeros. So I could either have 4, that means I cross over the x-axis 4 times, or I could cross it 2 times, or I could actually not cross it at all. Okay, how can I not cross over the x-axis at all? That means what? That means my whole entire function is what? Is sitting way up above the x-axis or just below the x-axis. Okay, so in this particular case, we have 2 positive real zeros because we already find out I don't have any negative real zero. Now, in other lecture videos for 4.3, I'm going to show you how the square rule of sine and other theorem can really help us along the way finding the zeros. Okay, so there's quite a few more stuff that can that I'm going to introduce you before I show you the steps on how to find the zeros. Okay, the ultimate way. So I just want to use this example to demonstrate that even though I can have 4 or 2, but 2 minus 2 can also tell me that I could have 0. If I have, let's pretend if I got 6, okay, I can do, let's say if I have 6 different sign changes, I can have 6. I could actually cross over the x-axis 6 times, or I could cross over 4 times because I'm minus 2, or I can cross it 2 times, or I can actually cross it 0 times. Okay, so if you just subtract 2 at a time, because 2 is an even integer, okay, that can actually help me. Okay, these are all or. It don't all happen at one time. I don't think I have an example x to the 6th power because that's a little bit redundant. Alrighty, so I'm going to conclude this video here. Okay, in the next video we're going to begin to talk a little bit about the intermediate value theorems and the types of zeros we have. Thank you for watching.